Alright, this is going to be a quick review of relations and functions. As you may recall, a relation is just a relationship between sets of values. In math, the relationship is between the inputs and outputs of a set of ordered pairs. The set of all possible inputs is called the domain, and the set of all possible outputs is called the range. Now, there are four ways a relation can typically be represented: as a set of ordered pairs, a table, a graph, or a mapping. Let's take a look at the set of ordered pairs. This first ordered pair tells us that when the input is 1, the output is -3. When the input is 5, the output is -4, and so on and so on. We can represent this in a table by listing the x values and the y values associated with those x values. So this table contains the same information. When the input, or x, is 1, the output is -3. When the input is 5, the output is -4, and so on. We can graph this information on a coordinate plane by plotting these points. So when the input is 1, the output is -3. When the input is 5, the output is -4. And when the input is -3, if you notice there are two outputs here. One output is 2, and the other output is -4. So the input -3 has two outputs. This can best be seen in a graph or a mapping, where we can easily see how the inputs, or the x values, are mapped to or associated with the outputs. So here 1 is mapped to -3, 5 is mapped to -4, and the input -3 is mapped to two outputs, 2 and -4. Now, a function is just a special type of relation where every input is mapped to only one output. So over here on the left, we have a relation that is a function. Each input is mapped to only one output. 1 is mapped to 7, 2 is mapped to only 9, and 3 is mapped to only -5. Now over here on the right, 1 is mapped to 7, 2 is mapped to 9, but 3, the input 3, is mapped to both 9 and -5. So this would not be considered a function, because when we input 3, we can't predict a single output since it's mapped to more than one. An easy way of thinking about functions is they are sets of data that make precise and repeatable predictions. In the relation on the left, the input 3 will only generate an output of -5 because it is mapped to only one output. Whereas in the relation on the right, the non-function, the input 3 could generate an output of -5, but it also could generate an output of 9. In this example, the input 3 is mapped to more than one output, so it would not be a function. So let's take a look at some relations, and we're going to identify whether or not they're functions. So here are 6 relations. Why don't you pause the video and try to identify which one is a function and which are non-functions, and we'll go over the answers in just a few seconds. So pause the video now. All right, let's see how you did. So the first set of ordered pairs, or the first relation I should say, is a function. 1 is mapped to only -3, 2 is mapped to only -6, and 3 is mapped to only -9. Whereas in the second relation, 1 is mapped to -2, but 2 is mapped to -2, but it's also mapped to 5. So when we input 2, we could get an output of -2, or we could get an output of 5. All right, so this would not be considered a function. Let's take a look at the tables. 1 is mapped to only 10, 3 is mapped to only 10, 7, 10, and 15 are also only mapped to 10. The fact that all of these inputs are mapped to the same output isn't relevant. The fact that they're mapped to only one output is. That's what makes it a function. We can predict what the output is going to be. If I tell you the input is 1, you know the output is going to be 10, because they're all 10. So no matter what we plug into this function, we're going to get out 10. That's predictable, so it's a function. Now, for number 4, all right, when we input 10, what are we going to get out? Well, 10 is mapped to 1, 3, 7, 10, 15. We can't predict the output here, so it is not a function. All right, so for number 5, we're looking at a graph. To analyze graphs, if you recall from class, there's a nice little test called the vertical line test. And we use the vertical line test because if you start at an x input, let's say 1, and you draw a vertical line down and then back up, if there's only one output, then you should only cross one point. And sure enough, if we draw a vertical line, we only cross one point. We can do that here and there and there and there and there and there and there. So this looks like it's a function. Every input has only one output. But in number 6, some inputs don't have one output. So for example, the input 1 is mapped to the output +1 and -1. The input 4 is mapped to the outputs +2 and -2. All right? And if we use this vertical line test, draw a vertical line, we intersect 2 different points, which means there are more than one outputs for that input. Now, since a function is also a relation, it can be represented as a table, graph, mapping, or set of ordered pairs. So functions can be represented just like relations. However, many functions follow a rule called a function rule, and this generates outputs from a given input. These functions can be represented using equations. Functions are often referred to as a machine that turns inputs into outputs. So in goes an input, it follows a certain rule, and out comes an output. And every time you input the same value, you get out the value that's mapped to it. So it's a machine that behaves well, or the machine that functions properly. So for example, y equals 3x plus 5. The function above calculates the value y by multiplying the value x by 3 and adding 5 to the result. So the variable x represents the input of the function and the value y represents the output. The expression 3x plus 5 is the function rule. So here's an example of data being generated using this function. So if our input is -2, let's drop -2 into the machine. In it goes. We plug it into x. 3 times -2 is -6. -6 plus 5 is -1. And out comes a -1. And that's why our output here is -1. And you can repeat this with 0, 5, 7, and any value that can go into the function machine. Now, function notation is a way of identifying and naming functions so we can easily work with them. It's another way of representing the machine. All right, function notation involves the name of a function, usually using a single letter like f. All right, the input value, which is often but doesn't always need to be x. All right, and then over on the other side of the equal sign, there's an output value, usually described by the function rule. So a few things. When you see an f, or when you're looking at function notation, this is a special symbol that means the name of this function, in this case f, all right, is a result of the input value x. So this is a function called f, all right, and it takes an input value x. And the output is over here on the other side of the equation. This is pronounced f of x. It does not mean a variable f multiplied by the value of x. So for example, in the function above, f of 14 would equal 13. And why? Because when the input value x is equal to 4, the function output value is equal to 13. So let's see if this works. So we're going to drop in a 4 into our function machine. All right, we're going to evaluate 3x plus 1. So 3 times 4 equals 12, plus 1 is 13, and out comes a 13. So according to the function rule, the output would be 13. So this is just an example of how function notation represents this mechanical process of generating outputs from given inputs. So let's practice using function notation. Here's a function called p, and it takes an input variable x. And it follows the function rule 3x plus 14. So if we wanted to evaluate p of negative 5, what we would do is plug in negative 5 into the function rule and evaluate. And as I said in class, you should always replace the variable with parentheses. So this variable, I'm just going to rewrite it with parentheses, and I'm going to plug in negative 5. So it's going to be 3 parentheses negative 5 plus 14. And that's what I get right here. 3, negative 5 in parentheses, plus 14. And now we can evaluate and simplify. 3 times negative 5 is negative 15, plus 14 is negative 1. So p of negative 5 is equal to negative 1. You drop in a negative 5 into the function machine, and you get out a negative 1. Let's try p of 0. We plug in a 0. We get 3 times 0 plus 14. That would be 0 plus 14, which is just 14. So p of 0 is equal to 14. And finally, p of 4 would equal 3 times 4 plus 14, which is equal to 12 plus 14, which simplifies to 26. So p of 4 is equal to 26. Here's a function h of t, and it is equal to or follows the function rule negative t squared minus 5t. So what I'd like you to do is pause the video and try to evaluate what h of negative 2, h of 0, and h of 7 might be. Pause the video now. All right, let's see how you did. So if you didn't use parentheses, all right, you probably ran into some trouble on this first one because you have a negative 2. So what I like to do is I like to look at the expression and just analyze it symbol by symbol. So what I'm going to write is a negative sign. Here's my variable, so I'm going to write parentheses with a negative 2 in it, squared, exponent of 2. Here's another negative sign or a subtraction sign, the coefficient 5, and over here another variable t, so I'm going to replace that with parentheses with a negative 2 inside of it. And when I do that, what I get is negative 2 inside parentheses squared minus 5 times negative 2. So negative 2 squared is positive 4, and we're making that value negative, so that evaluates to negative 4, and negative 5 times negative 2 is positive 10. And when you combine those two, that simplifies to 6. So h of negative 2 is equal to 6. H of 0 would be equal to 0, and h of 7 would be equal to negative 84. So now what we're going to do is we're going to use functions, or we're going to compare functions. So what I'd like you to do is use the functions above to determine if the following statements are true or false. So here we have two functions, g of x is equal to negative 2x squared plus 3, and m of r is equal to r cubed minus 6r. Now, is it true that g of 5 is less than m of 4? Is it true that g of negative 2 is less than m of negative 2? And is it true that g of 2 is greater than m of 2? Some are true, some are false. Pause the video and see if you can figure out which ones now. All right, let's see how you did. So in order to determine whether this is a true or false statement, we're going to have to find what g of 5 is actually equal to. When you drop in a 5 into this function, what is the output? What is g of 5 equal to? And the same with m of 4. So g of 5, when we evaluate that function, we get negative 47. For m of 4, we get 40. So now, because m of 4 and g of 5 are equal to 40 and negative 47 respectively, we can use substitution and rewrite this expression as negative 47 is less than 40. And that is a true statement. Now, following the same process, we can determine whether these other two statements are true. So g of negative 2 is equal to negative 5. M of negative 2 is equal to 4. Using substitution, we can rewrite the original statement as negative 5 is less than 4, and that also is true. All right, for this next one, g of 2 is greater than m of 2. All right, we evaluate g of 2, and we get negative 5. M of 2 is equal to negative 4. Using substitution, we can create the statement negative 5 is greater than negative 4. And although 5 is greater than 4, negative 5 is less than negative 4. So that one would be false.